Hello and welcome. Today we're discussing India's semiconductor revolution, though the stocks, the opportunities, and the risks you must know.
Take a look at the modern global economy, and you will find it resting on a single, microscopic foundation. Every electric vehicle rolling off an assembly line, every artificial intelligence model processing data, and every smartphone in the world requires semiconductor chips to function. But the supply chain keeping all those systems online is dangerously concentrated. Right now, a single island, Taiwan, produces roughly 60% of all global semiconductors and a staggering 90% of the world's most advanced chips. This line graph plots the financial reality of that geographic bottleneck for India. Between 2017 and 2025, India spent nearly 12.5 lakh crore rupees importing semiconductor products. Without a domestic alternative, this trajectory pushes annual import costs to $240 billion by 2035. Every processor inside your local hospital's MRI machine and every memory module in your mobile phone is manufactured outside the country. Despite a massive explosion in domestic technology consumption, India's internal production capability for these components has remained virtually zero. In December 2021, the government launched the India Semiconductor Mission, deploying a $10 billion war chest. The mandate is entirely straightforward: stop the outflow of capital and physically build a domestic semiconductor manufacturing industry from scratch. State governments are aggressively competing for these projects, and analysts are projecting a $168 billion market by 2035. But to understand if this massive capital deployment will actually yield returns, we have to look past the headline-grabbing megafactories and audit the highly specific, fragile infrastructure required to keep them alive. At the very top of the semiconductor ecosystem are the full fabrication plants, known as fabs. The centerpiece of India's current effort is Tata Electronics facility in Dholera, Gujarat. This is a roughly $11 billion joint venture with Taiwan's PSMC, requiring thousands of tons of concrete just to stabilize the specialized manufacturing floors. Below the full fabrication plants is a secondary tier of manufacturing called OSAT, Outsourced Semiconductor Assembly and Testing. Companies like Kaynes Technology and American memory giant Micron have already established these sprawling campuses in Sanand to take completed silicon wafers, package them into protective casings, and test them for commercial use. The components coming off these early production lines are focused on 28-nanometer process nodes. In semiconductor manufacturing, larger nanometer numbers indicate older technology. These facilities are not attempting to build the microscopic, cutting-edge processors used in next-generation AI data centers. Building these top-layer facilities require immense upfront capital. The Tata-PSMC fab alone costs 91,000 crore rupees. Because the construction phase spans several years and the calibration of the assembly lines takes several more, the timeline for these frontline companies to recoup their initial investment and show a true profit is exceptionally long. The primary megafactories carry the prestige and the heavy subsidies, but they also carry the highest execution risk. The immediate lower-risk capital flows are quietly moving into the hidden supply chain, operating strictly beneath them. You cannot simply plug a semiconductor fab into a standard municipal power and water grid. Operating these pristine environments requires a daily intake of specialized industrial resources. This visual scale compares the required daily water intake directly against the footprint of a standard factory. A single semiconductor fabrication unit will consume up to 3 million gallons of water every single day, and standard municipal water is useless here. The liquid must be chemically purified to levels far beyond anything found in nature.
A single microscopic trace mineral or biological contaminant introduced during the washing phase will instantly destroy a batch of wafers worth millions of dollars. This biological reality creates a strict mandate for highly specialized industrial water treatment systems. Companies like Ion Exchange, India's leading water purification firm, are stepping into this gap. They provide the zero liquid discharge and ultra-pure filtration systems required to even switch the factory lights on. The cleaning process also relies on highly explosive ultra-pure gases like nitrogen and argon. Because these materials are highly hazardous, they require secure cryogenic storage on site. INOX India holds a near monopoly on this specific industrial storage equipment, making them an essential vendor for every new facility. These hidden proxy companies occupy a uniquely protected position in the ecosystem. Every time a new fab breaks ground, it generates mandatory, massive purchase orders for specialized water tanks and cryogenic storage. These infrastructure companies generate revenue regardless of whether the semiconductor factory they supply ever reaches profitability. Below the factories and below the water purification systems lies the foundational base of the pyramid. This is where the entire $168 billion projection faces its highest probability of failure. A modern fabrication plant consumes 169 megawatt-hours of energy annually. That is enough to power a mid-sized city. More importantly, it requires that power to be absolutely uninterrupted. A single momentary drop in grid voltage can halt a cleanroom environment, forcing operators to scrap an entire production run. Then there is the human capital deficit. To operate these facilities, India needs an estimated 500,000 highly trained professionals. Training a lithography engineer or a cleanroom technician takes years of specialized education, and the current domestic university pipeline falls significantly short of that target. The billions of rupees allocated for corporate subsidies and ultra-pure water pipelines operate on a strict prerequisite. If the regional power grids cannot guarantee absolute stability and the engineering universities cannot produce the workforce, the physical factories cannot operate. This timeline chart plots India's technological standing against the global leader. India's current manufacturing capability is anchored at the 28 nanometer node. Taiwan's TSMC is already executing volume production on 2 nanometer and 3 nanometer chips. The manufacturing gap between those 2 points spans approximately 20 years of physical engineering and research. Closing that gap is exceptionally difficult because India is not competing in a vacuum. The United States has passed the $52 billion CHIPS Act, while the European Union and Japan are deploying their own massive subsidy packages to lure the exact same manufacturing talent and corporate investment. But looking strictly at Taiwan's technological lead misinterprets the financial mechanics of this bet. India does not actually need to manufacture cutting-edge AI processors to generate massive economic returns from this initiative. India's internal demand for electric vehicles, 5G telecom towers, and industrial automation is exploding. None of those sectors require 2 nanometer chips. They run on the older, highly reliable legacy nodes that India is building the capacity to produce right now, guaranteeing a massive captive domestic market for the chips rolling off these new assembly lines. When the first commercial made-in-India chips ship in 2026, they will not be the fastest on the market. But they will prove that a nation entirely dependent on imports can brute force a highly complex industrial ecosystem into existence, leveraging domestic consumption to permanently anchor itself in the global technology supply chain.
Subscribe to Dhansetu and turn financial knowledge into financial growth. Your journey towards smarter investing starts here.